In this lesson, we are going to be sketching polynomials based upon both the roots, the multiplicity, and figuring out the end behavior of a function. So first, we're going to kind of leverage what we learned with quadratics and with factoring and how we know that when a function, such as a polynomial, is completely factored, it is relatively easy to find the x-intercept. What you do is you look at each part of the factored form and you set each part equal to 0 and solve. So in this problem, I'd set this first part x equal to 0, and luckily that's an equation that's already solved as is. Then the second part, x plus 3, I'd set that equal to 0. Then I get x minus 1, and I'd set that equal to 0. And then I get the x minus 2 and set that equal to 0. And we would solve each one of these equations. Like I said, the first one's already solved for us, x equals 0. The second one, I'd have to subtract 3 from both sides, leaving me with x equals negative 3. The next one, I'm going to add 1 to both sides to get rid of the negative 1, isolating the x to get x equal to positive 1. And then finally, with the third piece, we're going to add 2 to both sides to get x is equal to positive 2. So these are our x-intercepts, which we gathered because it was factored. So that's going to be at x equals 0, x equals 1 to negative 3, x equals 1, and x equals 2. So this is going to be where the function goes through the x-axis. Now, for right now, we're going to kind of stop it there. We'll figure out end behavior in a little bit. We're going to move on to problem number 2. So problem number 2, same thing. I'm going to set each of those parts equal to 0. So the first part, x plus 5, that's equal to 0. Then I have x plus 4, that's equal to 0. And then I have x plus 1, that's equal to 0. Subtract 5 from both sides for the first part and get x equals negative 5 as one of our x-intercepts. Then we're going to subtract 4 from both sides for the second part, get x equals negative 4 as our second x-intercept, and then subtract 1 from both sides for the third part to get our final x-intercept of x equals negative 1. All right. So our x-intercepts are at negative 5, negative 4, and negative 1. For the next step, we're going to be talking about the end behavior. That is to say, if you look at a function's graph and you look at the function to the very far left and the very far right, those are kind of the ends of the function. So what we're doing is we're predicting or finding how the function is going to behave at those end values. We call that the end behavior of a function. Now, when we're looking at what's happening to the very, very, very far left of a function, for the most part, for polynomials, there's only really two options. Either it is really, really high up or it is really, really, really low down. So it's either trending towards positive infinity or it's trending towards negative infinity. So what we're going to do is you could plug in a number like negative 5 and figure out if it's above or below the x-axis. That'll work. That's a very algebraic approach to doing it. But what I'm actually going to do is I'm going to set x equal to find the left end behavior. I want to set x equal to negative infinity. So I'm plugging in a really, really, really large negative number. I'm looking really, really, really far to the left. And one of two things is going to happen. Either my answer is going to be positive because it's trending upwards, or it's going to be negative because it was trending downwards. So if I took negative infinity and I plugged it into this entire equation, realize all I'm caring about is if the answer is going to be positive or negative. So for this first part, the x, if I plug in negative infinity, that's just going to be negative. If I plug in a negative infinity here, I'll get negative infinity or plus 3. Plus 3 is not going to do anything to the negative infinity. It's just going to be negative again. And then I do that again for the x minus 1. That'll also be negative. And then I do that for the x minus 2. That'll also be negative. So in reality, I have a negative times a negative times a negative times a negative. If I have four negatives multiplied together, that's going to leave me with a positive. So as I go further and further to the left for this function, I'm going to be all the way up here. So I'm going to start with my arrow here. And then we can do the exact same thing again, except this time around, we'll do it for positive infinity. So if I do for positive infinity, then it's going to be giving me for the first term, it's going to be a positive. For the second term, that's also a positive. For the third term, the third part, that's a positive. And for the fourth part, that's also positive. And a positive times a positive times a positive times a positive is positive. So it's going to end in the positive direction as well. And now that I know how this function ends, both in the far left, the negative direction, and the far right, the positive direction, we can actually sketch this function because it has to go through our x-intercepts, which we calculated, and it has to end here and here. So I can do something like this. Goes through this dot. Oh, it's got to turn around to go through the next one. It's got to turn around again, and then it's got to turn around again. And there's a sketch of my function. Now, keep in mind, this is a sketch, it's not a graph, because even though we've got a lot of information, we've got the end behavior and we've got the x-intercepts, what we actually kind of technically are missing, but you would need calculus to figure out, is something like how far down does this part go? Does it go down that far, or that far, or that far? We also don't know how high up this goes. This is information that you gather through calculus. But for right now, we're not focusing too much on that. I just want a sketch. It's not a graph. It's not going to be the perfect rendition of what the function actually looks like, but it goes through the main key features. It goes through how the function's going to end. It goes over the x-intercepts, and those are the big two things that we're focusing on for right now. We're going to add one more layer after this. So problem number 2, same thing. If x was equal to negative infinity, then the first term would be negative, the second term would be negative, and the third term would be negative, which means it would be negative. So this one, far left, remember we're talking about when x is negative infinity, when it's really far to the left. When it's really far to the left, it will be negative, because a negative times a negative times a negative is negative. So it will start on the left side, it'll start in a negative orientation. But if x was equal to positive infinity, then the first term, x plus 5, would become positive. The second, the x plus 4 would turn positive. And the third, x plus 1, would also be positive. Positive times a positive times a positive is positive. So it will end in an upward trajectory. So next, I'm just going to sketch it, going through the dots that I've already gotten from the last slide for finding the x-intercepts. So it's going to do something like this. And that would be a sketch of problem number 2. The final thing we need to talk about is the multiplicity of a root and how that impacts the graph as a whole. So what we're going to do is we actually have the same problem multiple times. The only difference is the first root, that is when x is going to be equal to 0, I'm slowly changing the degree. That degree is called the multiplicity. So for problem number 1, because I have an x plus 2 and an x minus 2, I know that the intercepts are going to be at 0, -2, and +2. And if you were to do the end behavior, you would find that it does something like this. This is what number 1 would look like. Starts on the left side with an end behavior facing the negative direction. On the right side, when x tends towards a positive value, the end behavior is positive. And it goes through all 3 roots. But what happens if I take the 0 root? Remember, that's when x is 0. What happens if I change that root to have a multiplicity of 2 to be brought to the second power? Well, that's actually going to change the function in its entirety, because if you talk about specifically if x is equal to negative infinity, you would get Well, negative infinity squared, which is positive, and then this would be negative, and then this would be negative, which produces a positive. So first note that our negative infinity direction, how far we go to the left, it's no longer tending towards negative infinity. It's actually going to be tending towards positive infinity. Now that's not because this is a 2, but it has to do with the number of x's in this function, because there's 2 here, there's 1 here, there's 1 here. Because this is going to be a 4th degree function, that'll dictate end behavior a little bit more than this. What this is largely going to impact, what the degree is largely going to impact, is what happens here. Because this function still has x-intercepts at -2, 0, and 2. And the end behavior is still going to be positive on this side. When I go through the first x-intercept, nothing weird happens. I just go straight through it. What changes, however, is the root where the multiplicity is 2. At that value, which is right here, I am still going to hit that number, but because the multiplicity is 2, we're actually going to bounce off. We're not going to go completely through it. And then we go through the other x-intercept, which was normal, and end up at the end behavior. So notice when the multiplicity was 2, we bounced off of the root. Now, if it was coming in from the other direction, if it was coming in from up here, it would bounce off in this direction. So a multiplicity of 2 makes the function reflect off of the x-intercept. So now let's do problem number 3. Now first let's talk about, well, what's going to happen to the end behaviors. And if x is equal to negative infinity, then you're going to get a negative cubed, which is negative, and then a negative, and then another negative, which 3 negatives will make a negative. So this will have a negative starting location, and if you plug in all positives, it'll have a positive end location all the way to the right. Again, the first root is going to be normal. We're still going to cross through it. Now we're coming up to the weird one. If the multiplicity is 1, we would just go straight through it and behave like the red function did. As soon as the multiplicity becomes 3, it behaves a little weird. It's going to act like it's going to bounce off. So you notice it'll start to curve, almost as if it's about to bounce off. But it'll go through the other side anyways. So it almost acts like it's going to bounce off, but it goes through anyways, and then it's going to have to turn around to make it through this other x-intercept, and then make it to our end location. For the purple function, now we have a multiplicity of 4. If x is equal to negative infinity, you would get a negative number to the 4th power, which is positive. Then this would be negative, this would be negative, which produces a positive. So this is going to end positively on both sides. Again, it's going to go through the first one, and then the weird thing happens at the 0 location, but strangely it'll behave roughly the same as if it was a multiplicity of 2. Multiplicities of 4 and multiplicities of 2, they kind of behave the same. Next, we're going to be talking about multiplicities of 5. If x is equal to negative infinity, you would get a negative times a negative times a negative, which would produce a negative value. So it will start negative and it will still end positive. And now this function is going to go through the first dot, turn around, It's going to act like it's going to go through the second dot and behave just like the green function. Turn around, go through the other x-intercept, and end the same way. So when we have a multiplicity of 5, it behaves just like a multiplicity of 3. I'm willing to guess at this point you might be able to figure out what multiplicity of 6 is going to do. Now, if x is negative infinity, I'm just going to tell you, it'll be here. On the left side, it'll be at positive infinity. The right side, again, still the same location. So it will behave as follows. It'll go through the first x-intercept, and then, what do you know? It bounces off the x-intercept that has a multiplicity of 4, and it goes back up. What I'm hoping we're realizing now that I've done a bunch of different variations where I was just changing the multiplicity of the first value, that is the root at 0, is multiplicity of 1. Multiplicity of 1, you go straight through it. Nothing weird happens. Just go straight through it like it does any other x-intercept. Multiplicities of 2, 4, and 6, those are the ones that bounce off of the x-intercept. And then finally, multiplicities of 3, 5, 7, 9, and so forth, they're going to act like they're going to bounce off. So they start to curve like they're going to bounce off, but they go through anyways. Now that we have all that information, now we can finally get to graphing these functions in their entirety right off the get-go. So for problem number 1, I have x times the quantity of x plus 1 quantity squared times the quantity of x minus 3 quantity. So my x-intercepts, I'm not going to do the algebraic process, but I would say my first x-intercept comes from here. That's going to be x equals 0. Then I have this x-intercept, which is x equals negative 1 with a multiplicity of 2. And then the third part, I have x equals 3. So those are my 3 x-intercepts for the first function. So I've got x-intercept at 0, x-intercept at negative 1, and that's the one where I'm going to bounce off because of the multiplicity of 2, and x-intercept at 3. All right, so let's find the end behavior. If x was equal to negative infinity, then we would get the first part would be negative. The second part is going to be negative, but we're squaring it, so that would actually make it positive. And then the third part, well, if I plug in a negative for x, subtracting 3 will keep it negative. So I have a negative number times a positive number times a negative number. Multiply those together, and you will get a positive value. So for this function, it's going to start in the positive direction. If x was equal to positive infinity, well, we would get a positive times a positive times a positive, which is positive. So I'm going to end in a positive direction as well. So now we have all the information necessary to the graph. So I go through, I don't go through the first item. The first one at x equals negative 1, this is where my multiplicity is 2. So actually, for this first one, I am going to bounce off. Then I'm going to have to turn around so I can go through the next x-intercept. It is a multiplicity of 1, so I'm going to go straight through it. And the other x-intercept has a multiplicity of 1, so I go straight through it as well. And there's the graph for problem number 1. Problem number 2, we're going to do the same thing. So my x-intercepts for the first part are going to be at x equals 0 with a multiplicity of 2. And then I'm going to have x equals negative 4, multiplicity of 3. All right, so I got x equals 0, and I got x equals negative 4, which is right here. Let's determine end behavior now. So if x was equal to negative infinity, then I would be getting a negative 5 times a negative squared. Well, if I square the negative, That'll be positive, but then I'm going to multiply that by a negative. So actually, the first part's going to be negative. Then I have a negative number here, because a negative infinity plus 4 is negative infinity. It's negative. If I cube a negative times a negative times a negative is also negative. So I'm left with two negatives, and when I multiply those together, I will be left with a positive. So it will start in the positive direction. And then if, this one's going to be unique because all the others have changed or been the same, but this one's going to change. If x is positive infinity, yes, positive infinity squared is positive, but we're multiplying it by a negative number. So the first term is actually going to be negative. And the second part, positive infinity plus 4 is positive. A positive cubed is positive. And then a negative times a positive is negative. This is the first time actually where when you go all the way to the right, we're going to be in a negative direction. So now that we know where we're going to start, we know where we're going to end, we know where the roots are, and we know the multiplicities of the roots, we can now sketch this graph. So the negative 4 has a multiplicity of 3, so it's going to behave like it's going to bounce off. So it's going to go in kind of flat, but then it's going to go through anyways. And then the next root we are going to bounce off because it has a multiplicity of 2. So I'm going to have to turn around, and then I'm actually going to bounce off of that root. And then connect with my end behavior, and we are done with problem number 2. And then finally, problem number 3. I have x equals to negative 2. That's a multiplicity of 1 because it's to the first degree. X equals negative 1. Multiplicity 2. X equals positive 1. Multiplicity of 3. And then x equals 5. Multiplicity of 4. All right, so let's get those. Negative 2, negative 1, positive 1, and positive 5. End behavior, if x is equal to negative infinity, then negative infinity plus 2 is negative infinity, so this would turn negative. Negative infinity plus 1 is negative infinity, but if I square that, it'll become positive. Negative infinity minus 1 is negative. Negative cubed is still going to be negative. And then we have a negative minus 5, which is negative. So this is going to be all negative. But then I'm bringing it to the fourth power. If I have 4 negatives, that'll produce a positive. So of the 4 parts, it'll be a negative, positive, negative, positive. If I multiply these all together, these 2 negatives will become positive, times another 2 positives would become positive. So it's going to start on the left side, in the far left direction, in a positive facing direction. And then if x is equal to positive infinity, well, this would be positive, this would be positive squared, which is positive, this would be positive cubed, which is positive, this would be positive to the fourth power, which is positive. So we would just get 4 positive parts. And when you multiply those 4 together, you would get a positive. So it will end in a positive direction as well. Now that we have the roots, their multiplicities, and the end behaviors, we can now graph this. So the x equals negative 2, that's just a normal first degree root, so just go through it. Then at x equals negative 1, which is my next one coming up, I have a multiplicity of 2, so it's going to bounce off. Then the next root, which is x equals 1, has a multiplicity of 3, so it's going to act like it's going to bounce off, but go through anyways. And then the last root, which is at x equals 5, it has a multiplicity of 4, which means it is going to bounce off and then connect with my end behavior. And even though the graph looks a little funky, that is exactly what the sketch looks like, give or take its local maximums and minimums.